All right, so that's now that we kind of understand what's cryptanalysis and how it works, like differential cryptanalysis and so on, let's talk a little bit about statistics or probability theory to see why this works and what we can do. So let's look at one of the exercises I give as a thinking exercise, where you are given a dice and you are allowed to roll it to see the results as many times as you want. You are asked to determine if the dice you have is a fair dice or it's a biased dice which rolls 6 with probability 1/3. So what would you do? So most of you give the correct answer. What you can do is to roll the dice many times and see how many times you roll 6. Divide that number of observations with the number of trials, and this will give you the kind of a experimental probability of the dice rolling 6. So if it is close to 1/3, you will say that this looks like a biased dice. But if it is close to 1/6, you will say that it looks like a fair dice. But the question is how many times you should roll this dice so that you will be confident that it is really fair or biased, right? So this leads us to some definition. So here I will use some notation. So P is used for the probability of the distinguisher for the wrong key. But if you are at the distinguishing level, you can also think about this as the probability of observing an event for a random permutation, and P0 for the probability of observing the distinguisher for the cipher, the secret key you don't know. But at the level of attack, we said that there's a wrong key randomization hypothesis. So all of the wrong keys act like random permutation, and the correct key acts like the correct key, of course, with probability P0. So assume that we found a distinguisher for the cipher, okay? So that distinguisher is observed with probability P0 for the correct key and probability P for the wrong key. So I need to introduce a few more terms, like PFA, false alarm probability. In this scenario, you say that this is the correct key, but actually it is a wrong key. So you have a false alarm. Also non-detection, you perform the attack, but you cannot find the correct key, okay? So we want this probability so small so that the attack works. So another parameter is N. This is the number of plaintext ciphertext pairs used to perform the attack. If you look at the previous slide, this N is the number of times you roll the dice, actually. So T is the threshold used to decide whether the key counter is the candidate. Okay, so this is, we said that in the dice example, if it is close to 1/6, it is fair. If it is close to 1/3, it is biased. So we kind of put a line between these probabilities. So saying that on one side, I will say it is fair. On one side, it is biased. So that threshold is T. So we can look at this problem in two different ways. One problem is that you already found the distinguisher, P and P0. You have the probabilities. And you say that you are going to perform the experiment N many times. So you choose N. P and P0 comes from the distinguisher you found. So question is, what is the success probability of the attack? Just by looking at these numbers, can I calculate my success probability? Another way to look at it, if I find the distinguisher and I know the probability is P and P0, if I manually select probability of non-detection and probability of false alarm, like 1/1000 or 10,000, then the question is how many pairs I need to perform the attack so that these probabilities hold. So in order to calculate these probabilities, we have to look at the problem as the binomial distribution and the summation of the following terms. So we have n pairs, and the distinguisher is observed with probabilities P and P0. So we are trying to distinguish two binomial distributions with parameters NP and NP0. However, it is computationally infeasible to calculate the non-detection or false alarm probabilities. For example, for the non-detection, the probability is the summation of these probabilities summing from I equals to 0 to T. This small n actually should be capital N, by the way. Sorry for the typo. But the problem is that you can do it for small values, like rolling a dice. But in cryptanalysis, here the capital N is close to the block size, 2 to the B. And probability P0 is also close to 2 to the minus B. So it is not, computationally feasible to calculate this. So here you need to perform some estimates. So one way is to estimate the binomial distribution is to look at it as a normal distribution. Alaaddin Selçuk used the fact that binomial distribution can be approximated by normal distribution when n is large enough. His formulas provide good success probability approximations for differential and linear cryptanalysis when you provide the inputs n, p0, and p. So in many cryptanalysis papers, you can see that they are citing Alaaddin Selçuk's paper saying that we chose n like this. P and P0 comes from the distinguisher, and Alaaddin Selçuk's formula says that it works with a success probability of 93% or something. Okay, so you can do this, or you can look at Blonder-Gertlich paper, which uses approximations for binomial distribution. Their algorithm takes the inputs P, P0, probability of false alarm, probability of non-detection as input, and provides you n, number of trials you need to perform, and threshold t, where you try to use it to distinguish the results. Okay, so instead of calculating everything again and again, you can simply use these estimates and obtain the results. But again, as you can see, everything starts with a distinguisher. First, you need to find the distinguisher to know this P and P0. Then the rest is finding the attack. But without the distinguisher, you cannot do that.